that proving if a set of, if given some axioms, like in mathematics that we have some axioms, then there is a way to prove any formal statement that we do with mathematics. And then remember that I was explaining that this is very similar on language to talk about this paradox, liar's paradox, in which I say I am lying, and this is a sentence that cannot be neither proof neither disproof, okay, which means that the language is not complete. So though we have this kind of logical sentences with the language, I can construct a sentence which is not be proof, cannot be disproved, because if I say I'm lying and it's true, I'm not lying, and if I'm not lying, I cannot say I'm lying because I'm saying the truth. So, and what Hilbert was asking is if there is an algorithm, so a set of instructions, whatever this set of instructions is, this is not so important, except that one has to optimize, okay, this algorithm. But for this moment, so when Hilbert was formulating that, there were not computers, there were not anything. So he was convinced that there is possible to find an algorithm that with this set of axioms that they are in mathematics, all problems in mathematics, any kind of problem, but for instance, we're putting as a typical problem, these decision problems, yes or not, it's this prime number, answer yes or not, can be solved, okay? And then indeed, very importantly, it was Church and especially Turing, okay, in 1936 that they give a negative answer. So there are problems that they don't have an algorithmic solution. In other words, there are problems that we cannot solve in mathematics, and it doesn't matter which kind of computers they are, they will never be able to be solved because mathematics is not a complete theory with a set of axioms that we have. Okay, so there are three kinds of problems that we know, problems that we know how to solve them, so we know how to create an algorithm. Problems that they have a solution, but we don't know how to solve them, this exists, okay? And problems that they don't have a solution. And on this kind of thing, it went all this complexity theory that it has to be formalized, okay? And in particular, no, this was the existence of there is this non-polynomial kind of complete set of problems, okay? This kind of problems that I didn't explain it the other day, but it's a kind of problems that, for instance, is this kind of the salesman problem. Okay, so you have a person that it has to sell some product in a city or in several cities near your area, and you ask which is the shortest path that this person has to do in order to be efficient on solving this problem, this product. And of course, if you start to have many cities, okay, which are randomly distributed, to find which is the shortest path that connects all the points, this problem, it's NP hard, cannot be find the solution. So this NP complete is non-deterministic polynomial time complete. And then we have these problems that it was this kind of problem. So which kind of problems we have, no? So we have decision problems. Well, and then I will be here, okay? So we were saying that decision problem, this is this kind of problems that, for instance, I have a graph, as you see here, okay? And in this graph, I'm asking myself, the question is this, for instance, these two vertex on the graph, are they connected or not? And the answer is yes or not, okay? And again, if the graph is very difficult, it's very complex, this problem can be super hard, very difficult, okay? Can be solved. And then there is other kind of problems, and this is what we were talking about, which are these functional problems the last week. And these functional problems, we were saying it's a little bit different because the question that we will say here, so, and this is when we have to create also these algorithms, okay, and this is technically called this min path problem. It's given this vertex now that I have as before. Now I'm asking myself, okay, it's this vertex, this one and this one, which is the shortest path that connects these two vertices. So now we have that before in these decision problems, the output is yes or not, independently of the number that I put. No, I give you this problem. It's this number, a prime number. This is the problem. Okay, and then the answer is yes or not. So I have always the same output for any input that I put, where the input is the number. And in these functional problems, which is like calculating a function, okay, now I can have a single output for each input, because now if I change these two vertices and I choose other two vertices, for instance, this one, okay, and this one, so the solution, which is the shortest path to go from the vertex 12 to the 30 to the 10th, no, 13 to 10, then that will depend every time on the vertices that I have choose. Okay, so this is a decision. And with this introduction, what we were doing, which is very important, okay, it's to define how one defines a problem. Okay, so how can mathematically one think what is a problem? Okay, and we say, well, the thing that we have to define, it's, okay, we were saying in another way, we are giving an alphabet, okay, which here, this alphabet, I was saying the other day, this alphabet is, for instance, this one, okay, 0 and 1. Now I'm giving words on this alphabet, which is here. This will be rather the words, okay? 0, 1, 0, 0, 0, 1, 1, 0, 0, all the words that I can do. So it's infinite. This is the entry set, okay? It's infinite. I can create as many words with this alphabet that has only 2 letters. And now I give a property. And with this property, I create a language, okay? And the language is associated to a property P. Okay, so what is a language? And this is the thing that I was explaining, and it's very nice. So a language, okay, is all possible words, okay, that, so X, which is the possible words that I can have, okay, such that these words belong to this language and fulfill this property. And we were giving this example that, for instance, in English and in Kinyarwanda, the letters are more or less the same. So we have this Roman alphabet that we are using, okay? And now we have many words. And now the property will be that of the words that I have, that I can create infinite words with the 27 letters that I have in the alphabet. With 2, I can create infinite. With 27, I can create, obviously, infinite, because I can have any sequence. Of course, in our languages, we don't have words which they have 200 words, because we will not be able to read it. But anyway, the idea behind it's very similar. And the question is, I do a random combinations of the letters of the alphabet, and the property will be, is that Kinyarwanda or not? Okay, and that will define the problem. Okay, so we were saying that to find the solution of a problem, we can always mathematically think that finding the solution of a problem is equivalent. This is very nice. So to find the solution of a problem, it's equivalent to say if a words belong to a given language or not. Okay, so we give an alphabet, we give all possible words that we can do with this alphabet, we give a property that defines a language, and now I solve the problem. It's this prime number, it's this number that I'm giving you created with zeros and ones, prime or not. This is the property, okay? So what is the solution? The solution is to see if the number that I'm giving to you, okay, it's a word which belongs to this language. This is how we have to formalize it, okay? And so there are several ways to, and this is how we have to understand these things of the algorithm and on the Turing machine. And then we were reviewing a little bit what was this Turing machine, okay? And I was explaining by words, because I could not use the things that I have, but that the Turing machine, okay, it's a machine to compute any arithmetic operation, okay? So any algorithm. It doesn't matter, it has not related with the kind of computer that we have. And then we say that everything that can compute it via an algorithm can be computed via this Turing machine, okay? It doesn't matter. It can simulate, the Turing machine can simulate any other Turing machine. Therefore, this Turing machine, that it was kind of very primitive, that we were saying that I will review it now today a little bit, okay? Can simulate any other Turing machine, for instance, the computer that we are using, all of us in our house, okay? It is also a Turing machine. A supercomputer is a Turing machine. Quantum computer, when it is done, it will be a Turing machine. Okay, so everything that can be, since it computes an arithmetic operation, so everything, any computer that we have or we can or we will be able to create will be a Turing machine. We know that a priori, we didn't know it. Okay, so and we were explaining, and then I was so this Turing machine, I was saying that it's an idealization of a computer. Okay, and there is something which is very important, which is this Turing or charge Turing thesis, which is nobody has seen a counterexample, in which we're saying that anything that can be computed by a Turing machine, okay, can be computed by an algorithm. So these two things, a priori, they don't have anything to do. Okay, a Turing machine is a computer, and an algorithm is a set of rules that we have to solve a problem. Okay, and then there is this Turing charge Turing thesis, in which it says, okay, any algorithm that I can think about can I invent, can be computed with a Turing machine. Okay, so it's like that. And then we were saying what it's a Turing machine, and I had a little bit different of formalism when I was doing the other day. It doesn't matter, but you remember, or maybe you don't remember because you just saw it one time, but I was drawing something like that. Okay, I was saying that, and here is the same drawing, oops, that a Turing machine was something that it has here, what I was calling this finite set of states, this finite set of states. Then we have here a program, which is the algorithm that we are giving, and then we have this kind of head that writes and reads and write in a tape, and this tape, which is here written, was infinite long. Okay, and so it has these properties. So we say that this Turing machine, which looks very simple, but it's not simple, one has to think a little bit, okay, has a collection of finite states. So it's like if it has this alphabet, okay, which is a finite, okay, then it has a finite set of symbols, an initial state, and then this writing and reading algorithm. And then I wrote for you a very simple algorithm, which was a little bit tedious to follow, okay, which is not here, but which was calculating this function f of x equal to 1. And we wrote it with 7 lines of a program, okay, and all these lines of the program were, if you remember, like that. My initial state is in Q, initially I have my tape in S, then if I find something which is like that, it will be to a state in the tape, I will write X prime, and then I would have this S, and this S, which was +1, -1, and 0 was telling me, move the tape to the right, move the tape to the left, or stay where you are. This is the position, okay? This is what it's S, okay? +1, -1, or stay where you stay. And then we were saying that if the problem is a moment that the Turing machine stops, okay? It doesn't move, right? It halts for always. And this is the solution, okay? And so these are some examples. And the important thing was this of here that, okay, so this is the same that I say in a much plain language. If a problem has an algorithm, okay, I can write an algorithm for this problem. The problem can be solved by the Turing machine, or vice versa, okay? If there exists a Turing machine, so here it's, let's put it formal, such for all the words that belongs to the language, okay? The Turing machine halts, okay? And then the Turing machine decides, so it's decipherable. So this problem is solvable, okay? And what is important is this sentence of here saying that the construction on the bottom of this Turing machine is equivalent to an algorithm. This is the strong sentence, okay? So any problem can be solved if I can solve a problem. There is an algorithm to solve it. And if there is an algorithm to solve it, the Turing machine solves it. And then there is another problem, which is, okay, if there is an algorithm that solves this problem, whatever the problem it is, which is the minimal number of operations that this algorithm requires. These two problems, they are linked one to another, but one can know that, for instance, we know how to solve a problem with an algorithm, but if I ask you which is the minimum, or put me a bound, okay? So at least I need 7 operations to do that, or at least I need 27 or 208, okay? Sometimes this we don't know. So we don't know how to find which is the optimal algorithm to solve a problem. Okay, and then we were looking at kind of problems that, for instance, to have feeling what is these problems, okay? And we were saying, well, let's first talk about this problem, countable set. Okay, so I have a set of numbers, and I want to say that I said that the set is countable, either if it's finite, that it's clear, no? Because if it's finite, we know how to count it associated with a number, or it has the same cardinality as the integer numbers. Okay, so we have to ask, are the integer numbers countable or not? Okay, so we go to the Turing machine. Okay, and then we create that Turing machine, which I didn't explain here, and I will leave it there. But the Turing machine tells us that the set, okay, this set, it's countable. Okay, so as a result, which is very strong, but I didn't talk neither yesterday, but this is also one thing, it's that the set of computable functions that I can do is also countable. Okay, so there is a finite number. It is countable. It doesn't have to be finite. Yeah? Remember that countable will mean that it has the same cardinality as the integer numbers, the set of integer numbers, which is not finite. Okay, and then what is a set which is not countable? Well, a set is not countable if it doesn't have the same cardinality of the integer numbers. And then we can ask ourselves, question, it's the set of real numbers. Of course, this is a question which is very philosophical, but then we will ask things which are more important, okay? So can I solve this problem? Can I know if the number of prime, and it's the number, it's, for instance, problem, okay? It's the set of prime numbers countable or not, okay? So we don't know, no? So now we ask, is the set of real numbers countable or it's uncountable? Okay, this is one of the problems. And then the set of real numbers is uncountable. This is not as before, but if we use Turing machine, we will see, okay, that with this Turing machine, the machine will never halt, which will say, okay, every time that I find a real number, count it. Okay, so it will never halt. So the set of real numbers is uncountable. And now we want to know, so we have said the set of functions that can be solved with an algorithm, it's countable. And now we ask the same question as the set of problems that I can question, I can pose using an algorithm. And remember, problem is giving an alphabet of symbols, 0 and 1, to encode whatever, okay? And given a property, find if a given word that I can create with this algorithm belongs to this language or not, okay? So by construction, if we think like that, the set of problems that we can create, it's the same cardinality, the set of languages, okay? And the set of languages, okay, it's strictly speaking, has a larger cardinality, obviously, because that the alphabet, okay, that I can have. So the set of problems, this is uncountable, okay? So there is a lot of problems. If the set of the number of problems that I can pose, it's uncountable, okay? While the Turing machine tells me that the solution of the solutions that I will find, it's countable. So therefore, it's a way to say that there are many problems that cannot be solved, okay? So, which is this corollary, as the cardinality, okay, of the Turing machine, all the algorithm is smaller than the cardinality of the problems. There are decision problems, yes or not, which cannot be computed by a Turing machine. They cannot be computed by a Turing machine, they cannot be solved. Okay, so this is more or less what we were saying, and then I just will go over that, okay, and I want to put this transparency here, which is the classes of complexity. So, and then I was saying that in order to order now the complexity of a problem, okay, what I do, it's the following, okay? I see, okay, how many operations I have to do when I increase the input of the problem, okay? And I was putting as an example, these two examples, the addition of numbers, okay, and the multiplication of two numbers. And I was saying that the addition, so because we have this algorithm, which is Arab, which is very easy, so it doesn't matter. It's equally difficult to add two numbers that they have each number two digits. So it's equally difficult to add 5 plus 7, because of course this is very easy, and this, I hope today I don't get wrong, but we will do it like that, okay, and we do it like that, and this is how we learn it in the school. But if we want to do 201 and 7 4 3, we will do exactly the same, no? 1 plus 3 4, 4 4 9, okay. So the only difficulty on doing that is that I repeat the same operation that I did before for 2 digits. Now I have to add 2 numbers of 3 digits. So I have 3 times, okay, the difficulty that I had before, because I have to do 3 additions, okay. So how does the output that I have increases with the input that I have? Well, linear, okay, in this case. So it's a super good algorithm. So it's here, okay, it's this green, is excellent, okay. We have an algorithm to add numbers with this excellent. Then we have algorithms which are not linear, a little bit over linear, which is this green here, and we say they are good, okay? Then we have some which are the orders. All these things, well, this is order log n, order O1, order n. So up to here, this is more or less fine. And then we start to things that they don't go linearly with n. They are, so this is linear with n, no? This is this straight line. And then we have things which are of the order of n log n, okay? This still, we can do things here, but then already when we have things which are already polynomial, okay? So this is order n2, it starts to be very difficult, okay? Order 2 to the n, exponential, horrible, okay? So we cannot solve these things, okay? So, and how people in complexity theory decides if a problem is easy, difficult, and so on. So, well, with the same formulas that we have before, no? So with this definition, so we say that the language belongs to the class, for instance, is not polynomial if and only if there exists a Turing machine that decides, okay, the language in polynomial time. Okay, so, and then we can put all these kind of problems here. And so, for instance, this is one of the problems which is very difficult and very important. Okay, so this example, given a natural number n, determine if it has or not has divisors, okay, except itself. Okay. And then, well, the same, it's the SAT, find a circuit, so there is all these problems. And now we enter in this kind of problem that I don't want to show it. Okay, I will show it in more detail. And then we enter in another problem, which is this one that we are going to use very often. Okay, so given a number n, find the factors of n. No? And this is the typical thing. So the factors, that means 2 prime numbers that multiply and give you this thing. Okay, so if I have the number 15, so this will be 3 times 3, okay, and this we all know. So this is the factorization of 15. But if I give you a number, okay, which it has a lot, so a number n which has many digits, so the quantum machine, the Turing, machine can solve this, okay, can solve, okay, there is solution. And now it says that the order is this horrible thing, okay, which goes exponential. So it's out of business for us at this moment, okay, for the moment. Maybe somebody finds, because remember that what I say is that the Turing machine tells you that the problem has a solution, but this doesn't mean that it tells you which is the best algorithm you can do, okay? It's able to, so we can create maybe a better algorithm, but what I wanted to say here is that if we look at this thing of here. So this is exponential with n. So it's a problem that a classical computer, a priori, it's very difficult. Okay, will not solve it. And the whole thing of the quantum algorithm is that there is an algorithm. Okay, this is an algorithm which tells us that the efficiency of this algorithm doesn't go, it's not anymore exponential. It goes like log of n squared, log n, log n, whatever. Okay, but it's not exponential anymore. Okay, and this is very important. So what is the message here? So look, this is this factor. The other things I don't care. So what is the message here? The message is that the Turing machine tells me that factoring, which is a very difficult problem, okay, is solvable because there is an algorithm. So the Turing machine halts. Okay, the Turing machine tells us that the algorithm, okay, that the Turing machine finds is exponential. Okay, so it's very difficult to solve with a machine because it's exponential in the input of numbers. And this we know because if I give you a number of 3 digits to factorize, it will take you all this hour to do it. And indeed, it's so difficult to do it that all the encryption that governments or banks or credit cards or telephones they use, it's based in factorizing something which is called RSA, okay, because these are the 3, Rydberg, Shanoy, and I don't remember the name of the other person, okay, which is factorizing a 169-digit number. Okay. And this is so difficult that it can be broken, but it's very difficult. But if you give, for instance, nowadays, okay, digit 300 digits number, for instance, so I have a number which has 300 numbers on it, and I ask you to factorize to find which are the 2 prime numbers that multiply. So I know that there are 2. So these decision problems, it's very funny, no? Because they are very difficult in one direction and very easy in the other, no? So if I give you the 2 numbers that they factorize this one, it's very easy to check if it's true, because how do you check it? Multiplying, no? And we know that to multiply, it's very easy. But the other one is very difficult, okay? So if I give you a number, 2 very big prime numbers, I multiply them and I give it to you, and I construct with that a digit, which is of the order of 300, because we know prime numbers that they have this number of digits, I think. Probably at that moment, that was the highest number of digits that it was known. And I asked, use all the computers of the world that we all together work together, okay, how long it will take us to find which is the solution. And it's easy to see that the time that it will take us now with the computers that we have, it's higher than the age of the universe. So since this will require more time than the age of the universe for the moment, because maybe tomorrow somebody very intelligent finds an algorithm which is different, okay, so which is much more efficient. But for the moment, many people has looked at this algorithm. I mean, if one finds an algorithm which is more efficient, we'll get to start with more than $1 million of dollars, because this is one of the 10 problems that who solves, so they will get rich. But that will be much more rich because all the encryption that governments are using and so on are related to this RSA. Okay, and since quantum can do it better, this is one of the reasons, or maybe the most important reason, why there is a lot of interest in the world, okay, to look for algorithms, okay, which are better. So what a quantum algorithm or what a quantum computer, we will see what it is now, can do better is it cannot solve a problem that cannot be solved. Okay, so if there is a problem that the Turing machine tells this problem cannot be solved, and some of these problems are real problems, I was saying the other day, so one of problem which is undecipherable, okay, it's to say which is the ground state determined with precision, which is the ground state of a highly correlated system. And by precision, I mean that they have to have the digits with a precision better than some gap. Okay, this problem, it's undecipherable. Okay, so the ground state with precision of this strongly correlated system, so it means a system with a large number of parties, so I cannot diagonalize it, will never be able to solve it. We will not be able to solve it, not with our computers, not with a quantum computer, nor with a computer that it's created in 1,000 years. Okay, so So, and normally when we talk about the problems, we talk rather on this line of here. So this is how the computer science, they put this computation. I have no idea. I don't even understand it very well. Okay, so, but I would like to show it here. So this BPP, it's random, it doesn't matter. So more or less, we say like that. Okay, so there is a set of problems. This one of here, which let me show what I mean here. Okay, so these ones of here, which are polynomial, which can be solved with our algorithms in a time which is rational. Okay, then there is, it's believed that there is this kind of problems. Okay, so this line of here, okay, okay, which can be solved efficiently with a quantum computer. So this is this quantum computer. Okay. Then there is the class of problems which are non-polynomial, which believe they cannot be solved. Okay. And then this NP complete. Okay. Non-polynomial means that, well, it can be solved, depends on the size of the input, but this NP complete cannot be a priori be solved. And if one knows how to solve one of these problems, it will be able to solve all the others. Okay, and this is this kind of knowledge that it can change, but is a little bit how is the status. Okay, and now let me run over all these things, because this is not something that I want to spend the time. And okay, and I want to talk. So these are lectures that we deliver. Artur is a professor in the Barcelona Supercomputing Center, so which we work together. I'm directing this course here, and he's an expertise on these things. Okay, so and I would like to explain you a little bit what is the circuit model. Okay, so obviously we don't use Turing machines, and what will be interesting is to understand first of all what is a circuit model, how one constructs a circuit model, and how do you do it in the quantum case. Okay, and with that I would finish. So let's go to the how we are going to understand the circuit model. So we will believe that, well, I will explain what is a circuit model of computation, but this is how our computers work. No? So they have wires and we have gates, and then we organize in such a way that we can implement in a very efficient way whatever algorithm of the ones that we know how to do it. Okay. So in the quantum operations, and then we will see it, okay, from the formulation of quantum mechanics, we know that the quantum states, they have to be transformed by unitary operations. So if there is not any kind of dissipation and everything is under control, we know that the state psi, okay, oops. We know that the way that we know to another state psi prime, it's always by a unitary operation. That means that every time that we do a transformation of our states, we have to apply a unitary operation. Okay, and so what means in the language of computation is that we will use unitaries that they have to apply to arbitrary states in order to make information processing task. An information processing task will be transform states. Okay, so we will think that what is an algorithm, what it's a circuit is I give you an input, which will be a quantum state. I do some transformations of this input, okay, by mean of unitary operations, and I measure to know what I have done, okay? And so this is what we are going to do. So these are the three tasks that we have there. We have this formulation of quantum mechanics, and with these unitary operations, we apply these unitaries to arbitrary states, and after the unitary operation, we perform measurements. And this stage of here, what we are, so after that, okay, we do a measurement, okay? And after we do a measurement, we will have an output of the measurement, and remember that the output of the measurement, it will be so PM, okay? Which we will say, which is, okay, the probability that I get the output M from the measurement that I'm doing when my input state was psi, okay? And this, I will write it like psi, M dagger, M psi, okay? So this is how the quantum mechanics postulate tell us that it's the effect of a measurement, okay? And so this is let's put it like that. So this is a measurement, if you want, an operator, M of M, which has M outputs, are the outputs. Okay, and we know that quantum mechanics tell us that this is always probabilistic, so it's not deterministic, except in very trivial cases. So in some way, we can think that we can approximate that these quantum operations will be a little bit like doing random classical operations, a little bit, it will be not the same. Okay. So what is the goal in quantum computation? So to look for methods to create unitaries, global unitaries, because I want to do many things. So I have to create any unitary that I can do. I have to decompose this unitary, okay, as a function of gates. This we do very similar in the classical computation. Any transformation that I want to do, I have to do it by gates. And the number of gates has to be small, because if I have to implement for each operation a different gate, what it will happen is that I will have to have incredible chips, okay, with a lot of memories to do something different, and will be very inefficient, okay. And so we will do the same in the quantum operation. So we have a unitary that we want to implement, and then we have to find how many gates we have to, so let's say that will be applying gate, I don't know, n minus 1, gate n minus 2, whatever, okay, and gate 1 over my state, okay. So I want to decompose my unitary as a sequence of gates, and this I have to understand like that. Gate 1 operates, so the time goes in this direction. Gate 1, so this will be, I have my state psi, okay, and now I'm putting gate 1, gate 2, gate n, like that, okay. So I have my initial state psi, it goes through a gate, I have a psi prime, it goes to another gate I don't measure, and at the end here I will measure. So what it will be the goal? The goal will be that when I am in this circuit model in which I have just gates and wires, that the number of gates in which I can decompose a unitary operation, it's small, okay? And then I will measure. And it's important, I will not talk about here, but there are other methods which are also universal, okay? And this is adiabatic quantum computation and measurement-based quantum computation. These are two methods that they are proved to be universal, like in the circuit model, which is the only one that I'm going to talk a little bit. Okay, so how we have to check that it's universal, okay? So that what that means, it means that anything that I can do in one model, I can do it in another. And this is exactly how one does it in the classical model, no? In the classical, so our computers, or the way we are using now, okay, we have bit operations. And so we have to understand the bit operations as a following, no? So a bit is 0, 1. So we have my bit operations. So if I have a single bit operation, okay, which is, for instance, I don't know, then this thing of here, okay, so this is my input. So this small drawing, let me put it bigger, okay. So I have my input, A. I have a single gate, which I'm going to write like that, okay, because this is how the people work it, like in classical things, okay. And then I have this C, which is negation of A, okay. So my input, A can be 0 or 1, okay. So my input can be 0 or 1. So, and then, so I can have, obviously, 0. So if I have a single bit of operation, I have as maximum 4 operations, no? I can have that the input is 0 and the output is 0, the input is 1 and the output is 1, the input is 0 and the output is 1, and the input is 1 and the output is 0. There is nothing else, okay? 2 to the 2. So in this case, what is not negates, no? So if the input is 1, I'd have to do the opposite of 1. That gives me 0, okay? If the input is 1, that gives me 0. So this is not. Okay, and in the input is 0, not gives me 1. If the input is 0, okay, so these two things creates what is the negation gate, okay, which is like that. Okay. So in general, how many bits I have? Well, if I have one input bit, so I have a bit as an input, as a bit as an output, okay, and then I can have 2 to the 2 possibilities, 4 possibilities, 0, 0, 1, 1, 0, 1, 1, 0. Okay. So now, if I have 2 bit gates, okay, What doesn't mean 2-bit gates? I enter two things. Okay. I enter two things, and now I can have even one output and one input. Okay. So a priori, all possible combinations are 16. And this is the table that I have. So I have this 16. Okay. So, and now why I say that, of course, if I have 3 inputs, there is not need. Okay. So all classical gates can be done, although they are not universal. Okay. But it's easy to do it with 2 bits. All classical computation, we do it with 1-bit gates and 2-bit gates. Okay. And there is a universal set of 2-bit gates, which means that any operation that I can implement it, I can do it with this collection of gates, the collection, okay, which are universal. And so a universal gate set is a number. So how many do I need? Okay, of 1 and 2-bit gates that can reproduce all 1 and 2-bit operations, all possible ones. Okay, so I don't, of course, here is a lot of, have 16 operations. So how many do I need? Well, for instance, okay, I can have here the and. Let me write here. Okay, so these are the classical universal set of 2-bit gates. Okay, in the 1-bit gate, it's always not, which I have already written here. It's the negation. Okay, so I put here A, I draw it like that. This is, and here there is C. Okay, and I know that if here I put a 1, here I have a 0, and if I put here 0, here I have a 1. So this C is negate the value of the input of entrance. Now, if I look at the set classical, okay, I'm talking everything about classical. So this is the set of 2-bit gates, and you probably have here sometimes. So there is this NAND symbol, okay, which is the negation of AND. So AND is addition. So if I put an addition, I say that it will be a set that if the initial state, so I think I have put it here. The AND gate is, I don't know, but it's very easy and it's very important. So it's this kind of set, no? I have, okay, this is AND, okay? So if this is 1 and this is 1, okay, the output is 1. This is called, and otherwise, if this is not, the output is 0. Okay, so otherwise 0. And why is that? And because it's not addition, so is if this is A, my input A, and this is my input B, and it says if A and B are equal, if A and B are equal to 1, the output is 1. Okay. What is NaN? NaN, it's the one that negates, okay, the AND. So, and you can always rate it like that, not and say not, or nor gates and so on, okay? So we have typically these ones. If A and B are the same, put a 1, otherwise a 0, okay? Sure, okay, so, or, if A or B, this is the gate or, if A or B is a 1, as an output, give me a 1. Look that these are 2 entrants and only 1 bit of output, which is short, which is going to be very important. It's the negation, okay, or it's the addition of the short, it's the addition of A and B modulus 2. Okay. So, and these are universal, okay, for instance, and not, it's universal. I can create any other 2-qubit gates with these 2, okay? So, this is how you prove it's universal, and that's it. And let's go to the last part, which is the circuit model in quantum computers. So we are going to do exactly the same. We have to create gates. We have to see that these gates, I will have, which is the minimal number of gates that I can do in order to implement any operation, and that I can produce any operation using qubits with this kind of gates, and see if it's universal, okay? And this starts to be a little bit different from classical mechanics. And the first thing is because we know that quantum operations are reversible because they are given by unitaries. Okay, so I know that a unitary has to fulfill that u to minus 1 is equal to 1. Okay, so I can always apply anti-unitarian to go back, which is also a unitary operation. So it's u to minus 1, okay, because this is equal to u minus 1u. And so quantum mechanics is reversible. Okay, so that means that if I apply all the gates that I apply have to fulfill that they are going to be, I can revert this operation. And what happens is that in the classical setup, which is this logic, okay, and NaN, or XOR, negation. So all these these are Boolean logical. So I create a table of truth and I create this Boolean logical. Okay, this is not reversible. Okay, so it's not reversible, and we see it already. It's not reversible because look, it's very easy to see it's not reversible because I'm going to use a lot of gates in which I have 2 inputs and 1 output. Well, this I can revert it, no? It's going to be very difficult to revert it in a unitary way. Okay? Because the number of states, it's not even preserved. Okay, so it cannot be. Okay, so since this is the logical that we have in classical computers, which is given by this Boolean logical, it's not reversible, we have to think differently in quantum computing, okay? So we have to invent a new set of operations. So, and this new set of operations, it's what we are going to call them the quantum gates. A new set of operations are these quantum gates, okay? And moreover, these quantum operations are continuous. Okay, and that also happens in Boolean logical, in which we have 0, 1, 1. Because why we need continuous things? Because we know that in quantum now we have bits which are linear and therefore continuous superpositions of zeros and ones. So in classical physics we have that 0 and 1. Okay, but now we have a 0 and 1 in quantum. So this is classical, this is quantum, and we have any state, which is a superposition of 0 plus 1, okay, with alpha and beta complex numbers, okay? So, so we have these gates that allows us to do the superposition, so we can do these gates, okay? So how do we think about these things? Well, the thing that we think about that is, first of all, we look which are the 1 qubit quantum gates. Okay, so operations. And then we think in quantum mechanics, how we think when we are talking about all these things of quantum information. We take this Dirac notation, which is a very easy notation for matrix algebra, which is the way that you can do quantum mechanics in the Schrödinger picture. Okay, with wave functions. This is not convenient here. Or you can do quantum mechanics in quantum information with matrix algebra, much more on the Heisenberg idea of with the Dirac notation, which is who put the notation in order to use this algebra. Okay, so in this case, how are the operations? Well, the operations are 1 qubit operations. They will be matrices 2 by 2. These matrices of here. Whoops. Okay. A qubit operation will be a matrix. This is my qubit. As I was writing before, alpha times beta, alpha beta in the Dirac notation, and I will have an operation which is of this form. Okay, and here it's very bad. How it's going to be 2-bit operations? Okay, so 2-bit operations will be a 4 by 4 matrices, like it's here written. Okay, this is A, B, C, D, E, F, G, because this is, sorry, it was not right. A, J, K, L, M, N, O, P, okay, which acts on a 4-dimensional state, alpha, beta prime, so 1 qubit, 2 qubits, okay, and gives me something, okay. Well, here it was written in another way, or let's give the notation. Okay, so theta, that here it was written like, I don't know, but it doesn't matter, gamma theta, okay, and this will give me a transformation alpha, beta, gamma prima, theta prima, which all corresponds in my basis to 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so now we say, how are going to be these 1 qubit operations? This is our task, okay? How are the 1 qubit operations and the 2 qubit operations, okay, such that any operation, so which is the minimum number of 1-bit operations and 2-bit operations, that any possible matrix in 2 by 2, I can decompose it as a combination of these 1 qubit and 2 qubit matrices. So I want to find the minimal set, which is universal. So now we go to the 1 qubit. Okay, so let's start by the first part, the 1 qubit operations. Now, if you remember quantum mechanics, okay, that we said that any transformation which is unitary for 1 qubit, there is a basis, okay, of all Hermitian operations that we can do here, okay, and these Hermitian operations are the Pauli matrices plus identity. So we are going to consider the following gates. The Pauli gates, which correspond to a matrix which is X, so by X. Sorry. Here by X, I will mean sigma X, by Y, sigma Y, and by Z, sigma Z. So I have this, which I will call it like that. So this is sigma X, as you see. Okay. This is the Pauli gate, Y, it's sigma Y, the Pauli gate Z. Okay, this is Hermitian operation, so these are Hermitian matrices, so they are good matrices. I can use them. And then I'm going to put something which is very important, super important, and I wanted to put it like that. Hadamard gate, okay? And this, I will explain what it's doing. And then I will put 2 other gates, which are fundamental, which is this S gate, okay, which is a phase gate. It gives a phase if you are in the state 1 and doesn't give a phase if you are in 0, and the P/8 phase. Okay, so this 2. Okay, so these are the set of operations that they are going to act on 1 qubit. Okay, and if you know, you remember 1 qubit, something that I can represent in the block sphere. This is how I say that a qubit representation is better in the block sphere. Therefore, since all qubits are in the block sphere, what we see is that, of course, these 1 qubit operations, X, Y, and Z, what they are doing is rotations along the X, Y, and Z in the block sphere. Okay, and this is absolutely fine, and this is something that we like, because we know that doing these things, we can go from any point, okay, that I'm here, to another point, doing a rotation, if this is the Z-axis, for instance. Okay, if I rotate, so I can move this to another point of the block sphere. Okay, so that will correspond to do a rotation along the Z-axis, so it will be this one up here. And of course, I can do it around the X-axis and then the Y-axis. And what is the Hadamard doing? So the Hadamard gate that I put it there, both of them here, what it does is the following. And this is why it's very important, creates superpositions. And I told you that superpositions and entanglement are the basic ingredients. So imagine that I start by 0, okay, which is my 1, 0 qubit. And then now I do Hadamard 1 over the square root of 2, okay, of these gates. And all these gates, they have to be unitary, okay, over 1, 0. Okay, and this is 1 square root of 2, and this is 1 times 1, okay, and 1. Okay, so when I put as an input the 0, so I put 0 as my input, Hadamard gate, okay, what I will get is a superposition 1 square root of 0 plus 1. Okay, so I go to this plane of here, which is equatorial plane. When I do this rotation, okay, I go to one of these states of here. And this is very important because it's the gate that it's going to create superpositions. And now we have to think about the 2, and that's it. They are not more 1 qubit gates, okay? And not all then they are needed. So, but this is, they already form a set. With that, we have enough. Of course, I mean, this P/8, I can put it as applying it several times. I will get, or 4 times, I will get this phase gate, okay? But they are very important, so I keep both of them. And now we have to look the 2 gates set, okay? Control 2 qubit gates, okay? And now we have this thing that it can be shown that any arbitrary two any arbitrary unitary transformation, which means a matrix 4x4, which has to fulfill that u times u dagger, u minus 1 is equal to u minus 1, u equal to the identity. It has to be unitary, cannot change the length of the two qubit states, okay, can be expressed as a combination of this control NOT, okay, control NOT gate, control Z gate, and swap gate. Okay, so these are the two. And what this control NOT, and it's very important, what this control NOT gate makes, it creates entanglement. And this is the reason that we keep it as such. So it creates entanglement. You see this one, it doesn't create, it's a control Z. Okay, so all the elements are in the diagonal, but this one creates the elements are not in the diagonal. And then you can have swap, which swap means that if I have these two states, psi and phi, okay, and I swap, so I will get phi and psi. Okay, this is swap. And finally, in the quantum computing, okay, we will put all these. We have to put the measurement, okay, because what did we say? It's, you remember at the beginning, we say that when we create this circuit, we'll have to do three things. We have to put, for any arbitrary state, we have to be able to decompose any unitary as sequences of quantum gates in such a way that any unitary I can decompose with this collection of gates. So then I have to show that it's universal, so that indeed that happens. And then at the end, in the computation, what I'm going to do is to perform a measurement, okay? So the quantum circuit has to finish with a measurement, which is this kind of measurement, okay? And so I have several, for instance, here I have 4 qubits, no? This is an example of a quantum circuit that I put it here. So in this quantum circuit, for instance, I will put, and the first qubit perform Pauli X rotation, okay? On the second qubit, perform a Hadamard rotation, so it started in 0. This it will be a plus, because here I'm going to, the Hadamard will give me 0 plus 1. Apply now a 2 qubit gates, this is an example, between the 0 and the first, okay? And proceed with a gate. On the third, I'm applying a Hadamard again, and on the fourth, a Hadamard, and now I'm applying a set, okay, of C nodes, okay? This is this one, this control node, okay, where we have to think that this is the target and this is the control, and this C node, it's addition modulus 2, depending, so you create a table truth, okay, and which is, how do you get this matrix is just doing, okay, so you put the control and the target, 2 inputs and 2 outputs, and you say, okay, if the input is 0, 0, 0, 0, 0, 1, the control, I think I wanted to say fine, is 0, so it's modulus 2, so I add these 2. So the first one, the control, I leave it like it was, and the second one, I do the addition modulus 2 of, so 0 plus 0, modulus 2 is 0. 0 plus 1, modulus 2 is 1. 1 plus 0, modulus 2, the first one I recommend, and the other one, this is the C naught. 1 plus 0 is 1, and 1 plus 1 modulus 2 is 0. Okay, so this is the second. And this, you write it as a matrix. Okay, so you create the logical table, and this is what it's doing. And well, it's easy to see that this creates entanglement. And now when we have the quantum circuit, we have to do that. So this is a typical quantum circuit. So we define which is the depth of the quantum circuit, and the depth of the quantum circuit, it's how many gates do I apply for each line of the input. So I start and I look here. Okay, so I say, okay, I start, I have 4 qubits. Okay, now I got here, I have apply one operation in each qubit. Now I have here, I have apply a second operation in each qubit. Now I'm here, okay. I have 3 operations, and here I have nothing. This is the identity. Okay. And here I have done nothing, which is the identity, nothing, which is the identity, and this CNOT. Okay, so I have 4 lines. So this is a circuit which has depth 4. Okay, and sorry, and now I apply here, I forgot that, Hadamard to each of them as depth 5th, and now I measure and I have an output. This is a quantum circuit. Okay. And then what happens? Well, then you can do several planes, no? That says you can do measurement and conditional classical operations. So I measure, after I measure, I will have just a bit, 0 or 1, because after the measurement, the wave function has collapsed. And I have only an output, which is a classical output, or depends on the measurement M output, okay? And then maybe I can combine these things that I was doing with, and this is classical, all right? This is why it's writing like that. I can do some things, okay? Because this has measure, so this is not anymore a quantum bit, has to be a classical bit if I have measure, but still I can apply things of a classical bit. So this is quantum with a classical thing. Okay, so, and let me finish today now checking that indeed what is the universality of this circuit quantum model. Okay, so I have to check that it's universal. So, well, the first thing that I can say is that since I said that all possible quantum bits, they correspond to points in the Bloch sphere. Okay, so any pure, and we are only talking about pure states, okay, are corresponds to a vector which is in the surface of the Bloch sphere. So all possible qubits, 1 qubit transformations that I can do has to be equivalent to all possible rotations that I can do, so that all the points of the Bloch sphere that I can reach. And this Bloch sphere is a 3-dimensional model. Okay, so that means that if I apply X, Y, and Z, I can reach any point there. So the set of X, Y, and Z 1 qubit gates has to be universal. Okay, and indeed they are universal. So a way to do it is that any 1 qubit operation, okay, can be written as a combination of rotation along the Z, rotation along the Y, and rotation along the Z plus X plus some phase. Okay, because this will say, okay, rotate along the Z, go here, rotate along the Y, go here, okay, and rotate along the X, which is this axis of there, go there behind. Okay, so for instance. Okay, and then 2 qubit gates, okay? What do I have to do in order to find the universal 2 qubit gates? Well, that means that any unitary 2 qubit gates, okay, acting on that has to be expressed as a combination of the -1. Okay, so we can do it like that. And this is how we do it in this combination of the -1. This is just a little bit like that. So we check it that any combination of the -1 will correspond to the same effect that if it was this D gate. And then we end up with this result, which is the one that I wanted, which is important. Okay, we tell us that universal set of quantum gates in the quantum case. Okay, the universal set is 1 qubit gate and C0, any qubit gate and C0 are universal sets for quantum computation if I use qubits. Okay, so I don't need anything else. So I can construct any circuit that I want with 1 qubit gate, whatever I want. Normally I would use Hadamard and C0. Okay. And in order to check, why did I write all these sets of gates? Because we will use it. So why I say, well, if you only need 1, whatever you want, and a C0, why did I write all these 2 qubit gates and 1 qubit gates? Well, because we will use it, okay? And also because in order to check that, okay, so the relation, but I don't want to enter that because this is really a little bit more technical. But if I want to check that this 1 qubit gate, whatever 1 qubit gate that I want, and a C0 gate, it's universal, I have to see that I can approximate as close as I want any arbitrary with a finite set of these gates. Okay, this is the universality. Okay, and to check this universality, you have to use this T gate. That doesn't have any importance. Okay, so what else do we have to do? And now this is the kind of program that we have in this quantum computing. Okay, so first we have to decompose any unitary of D in a product of D minus 1 until we reach to 2 quantum sets. Then any gate as a combination of any U2. So first I want to apply this unitary, okay, which is in the dimensions, okay, in the dimensions. And then I want to say that this unitary in the dimensions, I can write it as a product of unitaries in D minus 1 dimensions. So a priori, I can iterate these things until I arrive to, I can apply any unitary in any dimensional space, finite, as a product of 2 unitaries in a 2-dimensional space. So this is enough. I have enough with qubits. I don't have to go to higher states, okay? And then every time that I get this U2 that I will have fine, okay? So I will go from UD in a D-dimensional space, so in C to the D, okay? As a combination of C2 over C2, sorry, C2 over C2 over pam pam. And then each of these gates, I have to write it as a combination of C nodes and 1 qubit, okay? And then the 1 qubit unitary, I have to decompose it as a function of S gate, T gate, or Hadamard. Sorry, I don't know if there is a question. Okay. And with that, I finish, okay? And I show that the computation is universal. And with that, I will finish. And I will say that in this case, okay, doing all this model of quantum computation, one can show that you can implement some algorithms for some problems that before using quantum computing were like here, okay, and that was not polynomial and therefore very hard to solve for a classical computer. With quantum computers, okay, what we see is that this problem becomes to a new class, which is this class that I say BPQ, okay, which is solving in a polynomial time, but a much better, and now it can be solved, all right? So before, with a classical computer was not polynomial, with a quantum computer, it's polynomial, but I'm not solving anything that I cannot solve. So which is the goal of quantum and why many people is looking for algorithms? Because we would like to find many, okay? So we know very few cases of that. We think it's like that, but we would like to find many algorithms that we can solve with a quantum computer in a way which is efficient that classically was not efficient, okay? And that's it. I think that this is quite a dense lecture. I think that I leave if there is questions or somebody wants to ask something in this last few minutes, I will be happy to answer. Thank you.
Okay, thank you very much, Anna. Yeah. So we'll take questions. Any question? I mean, okay, thanks, Valentin. I have a question. My question is, so what makes quantum algorithms difficult to
find?
Yeah, to find.
Because quantum algorithms are difficult to find because you have to be able, well, first of all, because it's not a translation of the classical algorithm. Okay, it's not that you say I have a classical algorithm. So how do we think normally? Okay, let me stop sharing, that I will see. How do we think normally? Okay, so in most of the cases, so we know how to solve something in some way classically. I have an algorithm adding. Okay, I put this algorithm of adding with this and another gate, and now I will do it quantum. Okay, instead of it doesn't work like that because quantum is different. So quantum is unitary, and in the classical one, it's not unitary. So these algorithms that we know how to do it classically, we don't know how to translate to quantum. So this is one of the difficulties. And second, that we want to find problems that we cannot solve efficiently, because if we can solve efficiently, so adding, we can solve efficiently with our computer. So why we are going to construct a quantum computer to solve adding? So it's very expensive. It doesn't have sense. Okay, so we have to find problems that they are in this outer class. And this is many people look problems which are in the outer class and look if they are able to find to move it into this reduction that I was saying. No, so this will be the big goal. So we are, so let me put it here that I wanted. So the big goal will be this thing of here. Okay, take a problem, which is, do you see now my screen? Now, take a problem, okay, which is here. So this is factorizing. This we know. This is Shor. This is fantastic. Okay, after Shor, but Shor is already 20 years old. It's 95, 30 years old. My God. And there are several others, but not so important. Okay. But here there is the set of problems that they can be solved, it's countable, and there are many. Okay, so try to find another problem which is outside P, which is interesting, and that it belongs to, so that outside. So it was before here in the, when the classical, if we only consider the classical, this class doesn't work, all right? So you want to take any problem that it was and say if really you can solve it with a quantum computer. It's not easy. It's not easy. Okay, so there are a lot of algorithms which have a component of quantum. Okay, but to find relevant algorithms, it's very difficult. It's very difficult because you have to think completely different. Okay, so you have to think unitaries. You don't have the same set of gates. You have to decompose everything with these gates. You start with problems which are not in dimension 2. Okay, so you have a problem which is in dimension D. You have to reduce it. And then you have to see if it's efficient, because this is related to efficiency on this algorithm also. Okay, so how long it took to solve it. So we are not talking this. We are mixing the two things. It's a nice question, because first we have to find the algorithm, but we know that the algorithm exists. Okay, because the Turing machine tells it exists for solving this problem. Maybe we don't know the algorithm even classically. Okay, but and then we have to solve it using quantum in such a way that the efficiency of the algorithm changes the efficiency. Okay, so it's not anymore it's not anymore non-polynomials. You know, it's kind of polynomial in quantum. It's super difficult.
Okay, yeah. I mean, my other question is it more efficient to use circuits instead of just the matrices? Why did some people use circuits when you can just use the matrices? Why do you use all these gates or write them in terms of circuits when you can just use the matrices?
Well, because the gates, because the better way to write all these formalisms of quantum mechanics at this level in quantum information is to use matrices. Why? Because we are all the time doing transformations, which are, you know, it's a matrix, and because algebra matrix is super nice and very convenient and very compact, and you use Dirac notation and then it works everywhere. If you want to do it with Schrödinger equation, you can do it, of course, but it's much more, it's the same, because it's the same. They are two formalists, so it's exactly the same, but it's much less operatively. This is one question, okay? Second question, you use all these things when you use the circuit model, but this, I didn't say it, but let me see, okay? So this is the circuit model, but of course you can do it with adiabatic, okay? An adiabatic, then you don't do it. So you prepare an initial state of a Hamiltonian, evolve this, so you will do it with Hamiltonians, and you will do it probably with Schrödinger equation if you want, and then measure. Okay, and this is also another way. This is adiabatic quantum computation. So you don't use circuits and model and wires, and it's universal. You check that whatever you do in one model, you can do it in the other. So it's not necessarily to use circuit model. There is another one, which is quantum measurement, which is more complex, but it's also universal. So you are not forced. It's like that.
Okay, thank you. Valentin has a question.
Yes, I have a question. So how can you narrate the group theory and the quantum computation? As I saw on the slides, there's one quantum operation where there is Pauli X, Pauli Y, and Pauli Z. So it seems like a generator of
If you think,
SU2.
okay, I think,
So how can we relate to them?
So how
well,
does
I
this
think,
relate to group theory? Yeah.
sorry, I'll say again.
I said, how does this relate to group theory? Because then she's Valentine is saying there's this SU2 group, right?
Yes, I
Yeah.
think, I mean, these three Paulis are different, but I'm saying that instead of doing this Paulis, for instance, okay, which is any rotation there, okay, which normally in the computers you have. So one thing is that, so these Paulis are three Paulis which are independent. So you cannot relate one to another because these are three Paulis which are independent. So you know that they are independent. Okay, so, but there are two things here. So normally in a quantum circuit, you will have X, Y, or Z. You will use it. Okay? This is one thing. And why? Because I'm saying that you can imagine that in the block sphere, so this is what I wanted to say here, in the block sphere, whatever you want to do, you can do it one qubit operation. One qubit operation is not enough for quantum computers. They are unitaries, which, so what is the message? The message is any unitary operation, I can write any unitary in any dimension. So any matrix, which is in dimension n times n, okay, I can decompose it as matrices of dimension 4 by 4 and matrices of dimension 2 by 2 and combine these matrices. Okay, this is the first message. Okay, so that means that any operation that I want to do, I can decompose it as a collection of 2 qubit gates plus 1 qubit gate in this qubit circuit. And now, which ones? Okay, so it's enough that I choose, for instance, I was saying this Hadamard and Synod. I don't need X, Y, and Z. Okay, I don't need anymore. Okay, so of course, any operation. So these are a little bit different concepts. So any matrix A, B, C, D, okay, which is a unitary and has to have some conditions and so on. Okay, I can write it with the help of the Pauli matrices and so on. But this is not my problem. Okay, so when I write a circuit, I will write very often. I would say, okay, there's a model of a circuit. I do here an X and here Y, okay, and here Hadamard. Okay, Hadamard already you see it's a combination of X and Y because I have to go.
Yes.
Okay, but so up to here, that's fantastic. Okay, what I'm saying is any operation, it will be enough that I use Hadamard plus Synod. I don't have to use it, but sometimes it will be better that I use X and Y. Okay, but universality means that this is the minimal set that I need, but it's enough with 1 qubit. Universality, it will be enough with X and Synod or Y and Synod. I don't need the three of them. Okay, does that answer your question?
Not totally. So what I was saying, for the quantum gate,
Yes.
and then there's Pauli gate. It seems like a generator of SU1 in the group theory.
Yes.
So I need to know what the relationship between the quantum computation and that group theory. Is it any relation? So why you need to take the why you need to take the Pauli operator?
I don't need to take the Pauli. What you are saying is okay. Normally, if I have SUN, okay,
yes,
how I'm going to implement it? So is
yes,
that what I'm asking? Yes, but this is what I was answering. Okay, SUN. Yes. I'm saying that okay, which is unitaries with a special group, so the determinant is equal to +1. Okay, so I don't need that even SUN, but let's say like one that okay, because this is this kind of rotations in higher dimension. No, so because I know that SU2, okay, are equivalent to O3, okay? This is what you are asking, okay?
Yeah.
What I'm telling you is the following, okay? Universality of the quantum computing tell me that if I'm starting in something which I did not, I need UN, okay? But even imagine that I take a unitary with a determinant equal to 1. This UN, okay, I'm going to write it as a combination, as a collection of UN-1 times UN minus U1 n minus 1, let me write here, okay? So UN or SUN if you want, that doesn't matter. I'm going to write it like U1 and of n minus 1, U2 of n minus 1. I don't know how many, okay? And at the end, U1 of n minus 1. I don't know how many here. I don't know, K. Okay.
Yes.
And now each of one, I will write it like K prime U prime of n minus. Okay. So it's acting in a smaller dimension. And at the end, I keep going, I keep going, I keep going. Okay. And at the end, I will write it as a combination. This UN, I will be able to write it as a combination of I don't know, many primes acting in two-dimensional, 2 qubits. Okay. A collection. So or let's call it U tilde 1, U tilde 2. So with a lot of quantum gates that they only act in 2 qubits. Okay. In 2 qubits. Plus, in order to be universal, still I have to add operations in 1 qubit. Okay. So, but you can do the same. So normally you see, okay, yes, this is O3, and then you say this is X, Y, Z. Okay, these are the Paulis and so on. But don't think like that in quantum. Don't think like that. Okay. What the quantum model tells you is that any operation that you want to implement in dimension finite, whatever it is, I'm talking only about finite dimensions, n. Okay, n equal to 1000 by 1000. I want to create a quantum circuit that it has to be unitary because I'm going to do with quantum. So quantum forces me to be unitary. Okay, so SUN is unitary, that's fine. Of dimension 1000 by 1000 with a quantum circuit that the only thing that is going to have its entrance of qubits and outputs. You can do it. This is what it's telling you. Okay, so it doesn't matter. Okay.
So I have another question about the when there is the circuit, where it contains the Pauli gates, Hartmann gates. So
yes, yes, what it tells you, okay?
Yeah, I need to know that operation. We need to operate left to right or right to left. For the figure, there is a diagram.
Let me see.
There is a diagram which contains the X above, not that one.
Here.
Yeah, here. So for this one. So here we have, around this, yes.
You write like that, okay? So, and you write, if you want to write, for instance, how do you write this? Think of here. Okay, this line. Let's write this line.
Yes.
Well,
yes.
This line
yes.
to some point, okay? Because of course I have a synod between two. I always rewrite it. So imagine that it was not like that. So imagine that I want to write, this is my initial state, and then I do an X Pauli, a Hadamard, okay, a Y, and a measurement, okay? And this is a measurement. I'm going to write that, okay? I'm going to write it like that, okay? So on this order, okay? So because I have to think, on 0, I apply an X, and I will have, let's say, state psi prime, okay? Then I have a Hadamard, I2 prime.
Yes.
Then I have a Y, I3 prime, okay? So I write it like that. This is my, I write it like that. Y, okay, H, X, the other way around. Apply of 0, okay? And this is will be 1, 2, 3, okay? So first apply X, then on my output apply H. So this is time, runs like that, but I write it in this way. First I apply X, then I apply Hadamard, and then Y, and then I measure.
Okay, thank you.
Okay. You're welcome.
Okay. So thank you very much, Anna. So please, Anna, you share your slides with me. We'll put the video online. You share your slides with me, and I will send an email to everybody to tell them where they can get the slides. It will be on one of our Google Drives.
Okay. Thank you very much.
Thank you very much. Yeah, thank you, Anna. Thank you, everybody.
Bye.
Okay, thank you.
Bye.
Bye.